Hi, my name is Stephen Shah. I'm with my partners James Thomason and Sonia Kular. This is our Stat 453 project presentation. COVID-19 detection using CT scans. So the goal for this project is to develop an object detection model which can successfully determine if a given subject is positive or negative for COVID-19 using data extracted from a CT scan of their chest and lungs. And over the past year, COVID has had a major impact on the entire globe. With over 3.1 million deaths already, this project is important because it's an opportunity to make a real impact on people's lives. Communities of lower socioeconomic status are especially at risk, and there's a clear struggle for physical resources like test kits, vaccines, etc. And so an image detection model could be really efficient in consuming resources because it doesn't need any physical swabs or containers, and it can also at the same time keep so many more people safe. CT scans are non-invasive tests that are enhanced versions of X-rays, and they provide a detailed information on the internal workings of an individual's chest. Chest CT is really crucial in a wide variety of scenarios, especially for processes like medical diagnosis. So for our data, we obtained 742 CT scan images of people's chest cavities, and 374 of these people have COVID. 397 of these people do not have COVID. Thus, our data was not paired. So, for related works, in a study done by the University of Waterloo, researchers utilized X-ray instead of CT scans to detect COVID-19. This is cool because X-ray is less expensive and more widespread than CT. However, it is less detailed. Similarly, in a study done by General Electric, we had researchers use deep learning techniques to diagnose spine disorders. And this is cool because they use similar techniques like us. However, we are using CT scans to diagnose for COVID-19. We ended up finding out that some of the original CT scans we had contained markings and labels sometimes, maybe left by the radiologist, but we didn't need them. So to combat this issue, we tested both grayscale and non-grayscale models. We decided to leave these marks and labels in and not edit them out. So the architectures we considered were LeanNet 5, AlexNet, and ResNet, with LeanNet 5 being the only architecture using grayscale. So for LeanNet 5, we use 64 by 64 pixel images, and it's grayscale, so it's not 3 channels of color like RGB usually, and it's just 1, so the image dimensions are 64 by 64 by 1. So I mentioned earlier that we considered several convolutional neural network models, such as LeanNet 5 or AlexNet or ResNet. However, the two models that we decided to use most predominantly were LeanNet 5 and AlexNet. Here we can see their architectures, and note again that LeanNet 5 was the only one that we applied a grayscale transformation to, while for AlexNet we used a non-grayscale model.
So what we used in this project were two different optimizers, Atom Adaptive Moment Estimation and Stochastic Gradient Descent, or SGD. And in Python, these are the implementations of these algorithms. So what you can see here is that Atom has three different trainable parameters, which are the learning rate, epsilon, momentum, and RMS prop. However, SGD has just one parameter, which is the learning rate over here. What you can see is that there are different advantages and disadvantages from both. From Atom, the default settings are typically optimal, so it's usually the second best of other classifiers and tends to be used as a default in deep learning. However, it requires a lot of memory for the state and typically doesn't do so well in terms of generalization, so it has a higher testing error. On the other hand, if we look at SGD, it does not need so much memory, just usually zero memory, so it's computationally friendly. Usually it gives us the lowest testing error. However, it can require a lot of time, tuning, learning rate, and epochs to reach the optimal solution, and we may get stuck. In terms of activation functions, we looked at sigmoid, rectified linear unit, and hyperbolic tangent. And sigmoid outputs numbers between 0 and 1. ReLU outputs numbers that are greater than or equal to 0. So if it's negative, it becomes 0. Otherwise, it's the original number. And hyperbolic tangent outputs numbers between -1 and 1 that are centered around 0. So sigmoid is usually easier to interpret. If it's 0, the neuron does not fire, but it fires when it's 1. For ReLU, it's a 6 times improvement in convergence compared to 10H and is very popular. For scaled sigmoid, it's usually preferred to nonlinear sigmoid function. But sigmoid may saturate and kill gradients, and there's a vanishing gradients problem that's also found similarly in the hyperbolic tangent situation. But ReLU units, on the other hand, can die during training, and the activation function can be unbounded and non-differentiable at 0. So there are advantages and disadvantages to these different optimizers and activation functions. And similarly to these different architectures as well. As Stephen mentioned, we've implemented these 3 different architectures, LayNet, AlexNet, and ResNet. We applied a 10% testing set, a validation set of 5%, training of 85%, a data loader batch size of 32, a random seed of 123, and we resized all our images to being 64 by 64 and applied a center crop as well. We also experimented with and without normalization and found that with normalization of our data tended to be better, and inside each of our layers as well tended to be better. Our data set came from Kaggle.com. It can be difficult to obtain CT scan data, but it's usually easier to obtain X-ray data, and CT scans can be very accurate, so we still use those. And this is a CT scan. This is a radiologist looking in between, like trying to identify like no COVID-19 or COVID-19 positive. And then there are these white speckles as well that are found a lot in COVID positive patients. And typically what our CNN is trying to do is to learn representations. This is a snapshot of our training data with COVID images, and this is it with COVID negative CT images. And we're trying to almost learn what would a radiologist learn when he or she or they are learning and making the diagnosis that somebody has COVID-19 or not based on their CT scans. That's what our model is trying to learn. And throughout, we use some variety of software and hardware. We use Jupyter Lab notebooks and these variety of these packages and code from Professor Raschka, and we're grateful for his help on this assignment as well. And we used Windows and an NVIDIA graphics card.
Hi, I'm James Thompson, and I'll be covering results, discussion, and conclusion. Pictured here are the results from the best performing model. The images were grayscale, not normalized, and a LynetTE 5 architecture was used with a ReLU activation function and an Atom optimizer. As you can see, the performance of 60.81% isn't much better than the baseline of 54%. The mini-batch loss, which shows the trend of learning in blue, just barely shows a trend of decreasing loss. This indicates that our model was not very good at improving itself. A potential solution would be to pre-train the model on another dataset. That way it's better at identifying features. The group learned from this experiment that not all datasets are equal. It was much easier to develop models in order to analyze things like the MNIST dataset. Remember, the MNIST dataset is several handwritten digits 0 through 9. It's clear that edge detection would play a role in identifying the number written. However, in the case of our dataset, we had images that showed CT scans of lungs, and although we aren't medical experts, as far as we could tell, the images showed no clear sign or indications of whether they were from patients who had COVID. Through our many experiments, we were not able to develop a model that was significantly better than the baseline of 54%. You could assume from this that the CT scans have no notable features. However, while that may be true, our dataset consisted of a relatively small number of samples with only 742 images. Had there been more images to draw from, the model might have performed better. Some interesting improvements that could be made to the model would be to research network architectures that work well with low sample sizes. In reality, with the increasing number of new strains and how varied symptoms are with patients, a neural network that just examines CT scans probably wouldn't be very useful, even if it worked well with the dataset we had. While many places struggle to get testing resources, the methods we use now seem much more useful than image recognition that identifies CT scans.